Assalamualaikum warahmatullahi wabarakatuh, and very good morning to everyone. So we're going to start our online mode lectures for this week. I just want to say I'm sorry because I unable to upload it on in the Spectrum since of the recent issues. Most of the UM's website already being down. I'm not sure when it's going to be up again, but I assure you that my lecture will be uploaded into the Spectrum once the website is up. So, just to recall back what we have learned so far from the last lecture on Monday. So we have here, we have done a weighted graph. We have done shortest path problems using Djikstra algorithm. And this is the Djikstra code. There are a lot of Djikstra code and programming because this algorithm is one of the well-established algorithm to find the shortest path or shortest route. Has been used extensively in wireless and network protocols. Okay, I promise you to show you how to solve this a problem of shortest path from A to Z from slide number 16. So we're gonna do one by one. So first we do a table here, vertex, start from vertex A, B, C, D, E, F, G, and Z. So first we put vertex A here, and we put a vertex A here, and then we just put vertex 0A, 0A, here you put 0, and then B is, from A to B is distance is 4, so you put 4 and you put A. And from A to C, you have this one for A. And then you have from A to C, you have distance 3. So you put 3. And remember to put A because this is coming from A. So the only adjacent vertex from A is B and C. So D is infinity, 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 and infinity. So this is infinity. It's just that it's very difficult to draw with mouse. Okay, now we solve A, B, and C. So from B and C, we select the shortest route, the shortest distance from A. So B, the distance is 4, and A to C, distance is 3. So we select C. So we put here C. Then this one will bring in here. Then we have 3A. So this one we just solve everything. Okay, 3A. So from C to B, okay, what we have 3 and A. Okay, from C to B is 3 plus 4, 7. 7 is more than 4, so we ignore it. We just still put 4A. Okay, C to C. And C to D is 3 plus 3 is 6. 6C. C to E is 3 plus 5, 8. 8C. So here you put 3 plus 3, 6. 6C. And this one E is 8C. 8C. Alright. And C only have vertex D and E and B. So we C is done here. So F, G, and Z is still infinity. So we look at the, okay, this one solve. This one solve for C. So we look at the 4, 6, and 8. Which one has the shortest route from C? So we have here 4, we have here B. So we put here B. And then we surround this one B, 4A. Okay, from B, what is the neighbor's vertex B? C already solved, so we only consider B to D. 4 plus 5 is 9. 9 is less more than 6, so we ignore, we just put here 6C. Then others E remaining 8C. And F, G, Z is still infinity. So between this one, B we solve here. So we have solved this part A, B, and C. A, B, and C. Oh yeah, D8C, D2. So we have here 6 and 8. Definitely 6 is less than 8, so you put here 6. 6 is column D, so we put here D. So here we put here 6C. And here is 6C. So D has a B, solve C, so B have, okay, from D to E is, you have 6 plus 1, 7. 6 plus 1, 7. From D to E. So 7 is less than 8. So you put here 7D. So we cut here and then we put 7D. Okay. And then we have D to F is 6 plus 5, 11. So we put here 11D. And D, we only have F and E. So we're done with D. We're done with D, so D is solved here. So between 7 and 11, we have, of course, 7, which is E, column E. So we put here E. And then we see what is the neighbor's vertex for E. So because D already solved here, I mean, this is the cloud. There's a bigger cloud here. D already solved. So you have here E2. E is the neighbor vertex is only G. So E is 7. 7 plus 5 is, so 7 plus 5 is 12. So you have here 12. 12E. So F maintain 11D. And E doesn't have route to Z, so only G. So between, okay, this one solve here. So between 11 and 12, you have F11. So F here, you put F. So this one 11D. Just put the arrow. Sorry for that. But you understand this is a D. Okay, wait. Should done better, I guess. Okay, sorry for that. Okay, 11D. Let's put that D, 11F, F4 solve. So for F, 11D, F can go to G is 11 plus 2. 11 plus 2 is 13. 13 is, 11 plus 2 is 13. 13 is more than 12, so you ignore that. So you put here 12E. So from F to Z is 11, from F 11 plus 7 is 18. 18F. Okay, so now we have F. So G and Z, of course G has 12, so G have shortest path from F, so you have put here G. Okay, G here, just put here G, here dot plus 12, 12E. Okay, from G to, okay, F we already settled here. This part we already settled. Okay, from G to Z is 12 plus 4, 16. 16 is less than, okay, G we put here 12E, and F we put here 11D. Sorry about that. So 12E and 11 is 18F. 18F. So from here you have 12 G to Z is G can only go to Z because F already done. So G to Z is 12 plus 4 is 16. 16 is less than 18, so we strike off 18, we put 16 G here. So here we have a 16G. So this is done, and this is 16G, the last one. Z. So no more. So if we want to trace back here, we want to trace sorry for that. Okay, we have to trace it, we put 16G. Okay, done. G and G is 12E. So 12E we go to E. So G is G12, 16G, we go to 16G, then we go row G and column G, we have 12E here. Sorry, this one is supposed to be here. I'm sorry, so 16G you have here, and then 12E. You look for G and G, column G and G. For 16G, you column G, row G. So you have 12E. So you look here, column E to E, 7D. 7D. Should buy a better laptop. Sorry for that. 7D. Okay, from 7D, you have 7D. You look at row D and column D. So you have 6C. 6C, you have column C, row C, 3A. 3A. There you have it. So you trace same column, same column and row. I hope you understand this. So you have 16G, 12E, 7D, 6E. So when you want to trace back, this one is Z. So you want to trace, you trace from backwards. You have A, C, D, E, G, and Z. So you want to put here, okay, you start from here, A to C, A to C, and C to D, C to D. So 3 plus 3 is 6, C. So C to D, D to E, D to E. Okay, have here D to E, and E to G, E to G, and G to Z. There you have it. So the path length is 16. Path length so path length is 16. So there you have it. this is the one you're using a Djikstra algorithm to find the shortest path from A to Z. So you have a table and also you write it down here. So you solve the Djikstra algorithm from A to Z. So okay, now we're gonna continue with the, okay, we already done the disturbing salesman problem. Now we want to go to the, we already have the planar graph. You already know the planar graph. Planar graph is not intersect with each other. So now we go to planar graph, homeomorphic graph. Planar graph in the subsection homeomorphic graph. Okay. So what is a planar graph with homeomorphic graph? First, we have to understand the elementary subdivision. Operation in which a graph are obtained by removing an HU to V, and adding the vertex W and edges UW and WV. Okay, what does it mean is, first you have two vertex U and V and you have one edge connecting them. So you just remove this. And then you add a new vertex W here, and then you join or you connect from U to W, the first vertex to W, and W to the second vertex. So instead of one edge, you have two edges. Instead of UV, you have UW and WV. So this is what it means by elementary subdivision. So what does it relate to homeomorphic graph? Graph G1 and G2 are termed as homeomorphic if they are obtained by sequence of elementary subdivision. So let's see, this is G1 and this is G2. So you can say that G2 is homeomorphic to G1. So this is really easy because even from our naked eye we can see that this is kind of similar graph. Again, homeomorphic graph, a more lengthy definition is, if you have G1 and G2, okay, you say have here H, and here you have G1, and you have your G2. So the loop-free undirected graph, G1 and G2 are called homeomorphic if they are isomorphic or if they can both be obtained from the same see the words here, loop-free undirected graph H by a sequence of elementary subdivision. So what does it mean? Okay, now you have H here. Let's say you have here H, and then you have here vertex A, B, what's that? Wait. So you have A, and you have B, and you have C, and you have D. So for G1, and this one is still A, B, C, and D. So you add another vertex. Let's say you remove the H, A, B, and then between A and B you add another vertex called O, and then from A to C you add another vertex P, and this one from D to C you add another vertex Q. So and then you connect A to O, O to B, A to P, P to C, and D to A and A to C. So this G1 is said to be homeomorphic to H. Sorry, G1 is homeomorphic to H. And again for G2 you add this new vertex, this, and this, and you have more edges, but this is homeomorphic to H and also homeomorphic to G1. So this is what I mean by homeomorphic graph, meaning that the graph can be traced back to the origin, or is a kind of a copy of same graph or maybe more vertex and stuff. So planar graph shows that what's the relationship between a planar graph? Show that the graph G1 and G2 are homeomorphic. So if they are homeomorphic to each other, they are planar. I mean, homeomorphic homeomorphic and planar graph is different. So shows that graph G1, G2, and G3 are all homeomorphic. So you have here solution. These three graphs are homeomorphic because all three can be obtained from G1 by elementary subdivision G1 for elementary subdivision. G1 can be obtained from itself by an empty sequence of elementary subdivisions. To obtain G2 from G1, we can use this sequence of elementary subdivision. So you have here G1 here. G1 here is the original graph. Okay, between A and C, you put a new vertex F. Between C and B, you put two new vertex G and H. And then you have here new HA. Okay, instead of this one A to C, only one H. Now you have AF and FC or CF or FA. And then you have, instead of one H from C to B, you have three H's. C to G, G to H, and H to B, and so on. So G2 is a homeomorphic to G1, and G3 also is homeomorphic to G1. See, this is easy. Even from our naked eyes, we can see that this is a homeomorphic. But the homeomorphic graph is not necessarily a planar graph. One theorem to prove that if you can find any graph that is homeomorphic to K33 or K5, K33 or K5, if you can find the homeomorphic of K33 and K5, it means that graph is non-planar. So K33, remember the K33, you have a bipartite, you have a set 1, and you have another one set 2. So a graph in set 1 and set 2 are not connected to each other, but as set 1 is connected to all other graph in set 2. So this is K33. And of course K5, remember complete graph, you have one vertex connected to all other four vertex and so on. So each vertex is connected to each other. So this is K33 and K5. Okay, the intuition is homeomorphism is like graph isomorphism after ignoring some of the degrees to nodes. Example, after ignoring nodes D, E, and F. After ignoring nodes D, E, and F in graph H is homomorphic to K5. So you have here S1 and S2 set 1 and set 2 K33, and you have here K5. If you can prove that any graph that is homeomorphic to K33 or K5, it means that the graph is non-planar. Some books say homeomorphic, some books say homomorphic, so but it has the same meaning. So the intuition is homeomorphism is like graph isomorphism after ignoring some of degree 2 nodes. Examples here, after ignoring nodes E, D, E, F in graph H is homomorphic to K5. So let's say this is graph G and this is graph H. If you talk about graph D, E, and F, which have a 2 degrees node. So you have F here, F has 2 degrees, E have 2 degrees, and D have 2 degrees. If you ignore all this, D and F, you can have this one, and this is clear a K5 graph, same, just that a different representation. So this is K5, and this is also a K5. K5 means that you have 5 vertex and all other vertex are connected to each other, means that like vertex A connected to 4 vertex and so on, just that this is a different representation. So again, Cross-Talkie's theorems say that if any graph is homeomorphic to K33 and K5, means that graph is non-planar. Okay, we go for the graph coloring. So what is a graph coloring? So when you have a map and you want to color it, such as there's no two neighbors regions or there's no two neighbors regions or state have the same colors, because you have to differentiate them in the map. So when a map is colored, two regions with a common border are Two regions with a common border are customarily assigned different colors. Like you have, if in Malaysia you have state of Penang and Kedah, so you have to color both the different colors, like Penang yellow or Kedah red or something. So we want to use the smallest number of colors instead of just assigning every region its own color. So the goal is how many? What is the minimum numbers of color that we can use to assign every region a unique, or sorry, every region a different colors. Every region have a mean every two regions or neighbors region does not have the same colors. So for color theorem, it can be shown that any two-dimensional map can be painted using four colors in such a way that adjacent regions or neighbor regions, meaning those which sharing a common boundary segment or not just a point, are different colors. So this is a four color map theorem. So someone have proved that in any map you only need four colors max. For that, no other two neighbors that have different colors. Okay, this is the map of United States. United States, you know, we have 52 or 51 states, I can't remember. So four colors are enough to show that, four colors are enough to show that no neighboring region have different same colors. No two neighbors or two adjacent state have the same colors. So like this one blue, and neighbors red, and neighbors another one is green, and so on. So you have this one. You have four neighbors. 1, 2, 3, 4, 5. So you have six neighbors. 1, 2, 3, 4, 5, 6, 7. Seven neighbors, but each have a different colors. So you only need four colors for your 51 states of United States of America. So you need only four colors, enough. So dual graph, what is dual graph? Okay, this is in the map. This is in the map representative. So you want from map, if you want to convert it to graph, you name it as a dual graph. Each map in a plane can be represented by a graph. Each region is represented by a vertex. Edges connect to vertices if the regions represented by these vertices have a common border. Two regions that touch only at one point are not considered adjacent. The resulting graph is called the dual graph. So you have here, let's see the map. So you have here vertex A, B, C, D, E, F, and G. And then you have vertex A here, and you have vertex B here, C, D, E, F, and G. And then vertex A is connected to vertex B, C, D, and E. Vertex B connected to A, C, and D. D connected to B, C, A, E, F, and G. D connected to everyone. So if you want to represent a map, you want to represent a graph from a map, you do it like this. So you check A connected to B, yes. A connected to C, yes. A connected to D, yes. A connected to E, yes. So on. So D is connected to everyone else. D 1, 2, 3, 4, 5, 6. Let's say F. F is connected to G, D, and E. F connected to D, G, and E, and so on. So this is also the same one. This is also the same one. You have BA. You have A connected to B, C, and D. C connected to B, A, D, E. Everyone. B connected to E, A, and C. And D connected to E, C, and A. And so on. So this is dual graph examples. Graph coloring. A coloring of a simple graph is the assignment of a color to each vertex of the graph so that no two adjacent vertices are assigned the same color. The chromatic number of graph is the least number of colors needed for a coloring of the graph. So chromatic number, what is the minimum colors needed in order for no two neighbors have the same colors? So what is the chromatic number of bipartite graph? Remember, bipartite you have two sections. That one section is connected to one section or one set is connected to vertex in set 2. So how many? So let's see, we draw here just a simple graph K2 3. So 1, 2, and 3. 1, 2, and 3. Ah, bear with me, sorry. So you have here vertex, this set 1, this is set 2. So if you color this one red, of course all other connector must be, let's say, blue. Blue and blue. So this one blue, this one you can color red. Okay, check whether any of the two vertices, adjacent vertices, have the same colors. So you check here. Okay, this one red connected to blue, 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 does not connected to red. So this has a different colors with its adjacent vertex. So you have check here red and also connected to blue, 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 not connected to red. So these have a different, I mean, the neighbors of this vertex all have the same, all have the different colors with him. So how many colors we need here in bipartite graph? Only 2. So we only need 2. Yes, 2. So the 4-color theorem. So we go back a little bit on the history. The chromatic number of planar graph is no greater than 4. This is what we have now. It can be said that it is true unless someone can can find fault or can find that this theorem is wrong. So it was originally posed as a conjuncture. It was really posed as a conjuncture in 1850s. So it's like 1850s, 1950s. It's already have it's already like 170 years old. It was finally proved by two American mathematicians, Kenneth Apples and Wolfgang Haken, in 1976. So it takes about 100 years to solve this. See, this, it looks kind of simple, but it's not really. So you take about 100 years. So don't be hard on yourself, you cannot solve any mathematical problem. So this is the first mathematical theorem that has been proven with the help of computers. They show that the theorem is false. That if the theorem is false, there must be a counterexample of one approximately 2000 types of graph. So you try 2000 types of graphs, they cannot find this false theorem. They use computer to show that none of these counterexamples exist. So the 4-color theorem still hold until now, unless one of you are genius that can find a fault of this 4-color theorem. So please contact me to publish a paper. Okay, what's the chromatic number of the graph shown below? So you have here A, B, C, D, E, F, G. So how many colors here you have? A and B doesn't have same colors. A and C must not have the same colors. So this one have 3 colors. D, okay, this one. So when with our naked eye, we can see this only 3 colors needed. 3 colors needed so that no adjacent neighbors have the same colors. So the chromatic number must be at least 3 since A, B, and C must be assigned different colors. So let's try 3 color first. 3 colors work, so the chromatic number of this curve is 3. Can it color by 2? No, because one A, B, C, this is triangle. Triangle means you need 3 colors because this is considered adjacent. You need 2 colors, purple and green. This one you cannot select green because it will be same colors with this one B. You cannot select purple because it's gonna be same colors with A. So you must need 3 colors for this one, for triangle. So what is the chromatic number for each of the following graph? Okay, let's say you write down this one, you write down blue. For its neighbors, you put red. Or maybe you want to put red here. Try 2 colors first, and then this one blue back, and this one red, and this one is blue. So see, A this one and this one doesn't have the same color, 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 and this one doesn't have the same color, and so that this one. So you can have two. The most unique, I mean the minimum number of colors is two. So like this one, let's say you put blue again, then you have red, then you have blue, and this one you have red. Of course you want to say this blue, but if this is blue, this blue gonna be the same color. If this blue, it's gonna be same like this one. So we can erase it. Sorry, okay, you have a BB. So this one you cannot use this one you cannot use the blue, so just another like green. So it match perfectly. Okay, you have need this one, you need a three chromatic numbers are three. Okay, this one white, yellow, white and yellow. And this one is white, yellow, and suddenly green. So that's it. Okay, that's why it takes about 100 years to solve, because this involves a very complex time complexity. The best algorithms knows for finding the chromatic. The best algorithms known for finding the chromatic number of a graph have exponential worst case time complexity in the number of vertices of the graph. So if you have more vertices, it's going to be more complex. And these have exponential worst case time complexity. Even the problem of finding an approximation to the chromatic number of graph is difficult. Just now you see maybe this like less than 10 vertex, less than maybe 20 vertex, still easy. But you have 100,000 of vertex like web services and stuff. How do you do this? But the four colors theorem still remains true until now. This explains why scheduling final exam is so difficult. How can the final exam at a university be scheduled so that no student has two exams at the same time? So you have here scheduling final exams example. How can the final exam at a university be scheduled so that no student has two exams at the same time? For instance, suppose that there are 7 finals to be scheduled. Suppose that the courses are number 1 to 7. So this one is definitely a height. Sorry, this one is definitely a vertex, not height. 1 to 7. So you have here 1 to 7, 7 vertex. Suppose that following pair of course have common students. 1 and 2 connect vertex 1 to vertex 2, and you have an edge. 1 and 3, 1 and 4, 1 and 7, 2, 3 until 7 and 6 and 7. So you have here 1, 2, 3, 4, 5, 6, 7. So you check 1, 2, yes, check. 1, 3, yes, check. 1, 4, and 1, 4 is check. And 7, 2, check. 7, 3 also check, and so on. So how do you do this? That's why this is one example of application of map coloring. You just put like a you just put a color, have that, okay, you put red here. Try not to make two adjacent vertex have the same color. So this one red, this one blue, this one green, and this one brown. So red here, you finish already done one cloud. So you have here one red, and you have here brown, and you have here green, you have a spider, you have a builders, and you have a brown 7. So there you have it. So you can schedule like red and red, blue and blue, green and green, and brown and brown. So you have red. Red is 1 and red is 1 and 6. Blue is critical response. Okay. Okay, there you have that. And then you try to make it time period. So the red and 1 and 6, time period 1, red 1 and 6. So take a different color here, red. Okay, this one red. Okay, now blue, we take a blue. So this one blue, blue is blue only one. So set 2, causes 2, time period 2, and then we have green here. Take some green. We take some green here. Then we take green here. And then we have a green 3 and 5, and then we have 4 and 7. We have 4 and 7 is brown. Do we have a brown? Yes, brown. So you can put here brown. So there you have it. You make a time period 1, cos 1 and 6, same day. 2, cos 2 on the same day of time period number 2, time period number 3, and time period number 4. So there you have it, scheduling final exam using map coloring. So this we finish the first half of our lecture. So we're going to come back for the second half of our lecture, which is a queuing theory. I can take a break now.